size and how decomposition evolved historically. So there are many derived units which we use in our daily life for convenience, and some are tailored to a specific field. We have centimeters, we have millimeters, kilometers, we have inches, feet, miles. Astronomers even use the astronomical unit, which is the mean distance between the Earth and the Sun, and they use light years, which is the distance that light travels in 1 year. We have milliseconds, we have microseconds, we have days, weeks, hours, centuries, months, all the right units. For the mass, we have milligrams, we have pounds, we have metric tons. So lots of derived units exist. Not all of them are very easy to work with. I find it extremely difficult to work with inches and feet. It's an extremely uncivilized system. I don't need to insult you, but think about it. 12 inches in a foot, 3 feet in a yard, that drives you nuts. I work almost exclusively decimal, and I hope you will do the same during this course, but we may make some exceptions. I will now first show you a movie which is called The Powers of 10. It covers 40 orders of magnitude. It was originally conceived by a Dutchman named Kees Boeke in the early 50s. This is the second generation movie, and you will hear the voice of Professor Morrison, who is a professor at MIT. The Powers of 10, 40 orders of magnitude. There we go. I already introduced, as you see, their length, time, and mass, and we call these the three fundamental quantities in physics. I will give this the symbol capital L, length capital T for time, and capital M for mass. All other quantities in physics can be derived from these fundamental quantities. I'll give you an example. I put a bracket around here. I say speed, and that means the dimensions of speed. The dimensions of speed is the dimension of length divided by the dimension. So I can write for that bracket L divided by bracket time. Whether it's meters per second or inches per year, that's not what matters. It has a dimension, length per time. Volume. We have the dimension of length to the power 3. Density. We have the dimension of mass per unit volume, so that means length to the power 3. All important in our course is acceleration. We will deal a lot with acceleration. Acceleration, as you will see, is length per time squared. The unit is meters per second squared. So you get length divided by time squared. So all other quantities can be derived from these three fundamentals. So now that we've on the units, we have the meter, the second, and the kilogram, we can start making measurements. Now all important in making measurements, which is always ignored in every college book, is the uncertainty in your measurement. Any measurement that you make without any knowledge of the uncertainty is meaningless. I will repeat this. I want you to hear it tonight at 3 o'clock when you wake up. Any measurement that you make without the knowledge of its uncertainty is completely meaningless. My grandmother used to tell me that, at least she believed it, that someone who is lying in bed is longer than someone who stands up. And in honor of my grandmother, I'm going to bring this today to a test. I have here a setup where I can measure a person standing up and a person lying down. It's not the greatest bed, but lying down. I have to convince you about the uncertainty in my measurements, because a measurement without knowledge of the uncertainty is meaningless. And therefore what I will do is the following. I have here an aluminum bar, and I make the reasonable, plausible assumption that when this aluminum bar is sleeping, long, then it is a lot longer than when it is standing up. If you accept that, we can compare the length of this aluminum bar with this setup and with this setup. At least we have some kind of calibration to start with. I will measure it, you have to trust me. During these 3 months we have to trust each other. So, I measure here 149.9 centimeters. However, I would think that so this is the aluminum bar, this is in vertical position, 149.9, but I would think that the uncertainty of my measurement is probably 1 millimeter. I can't really guarantee you that I did it accurately any better. So that's the vertical one. Now we're going to measure the bar horizontally, for which we have a setup here. Scale is on your side. So now I measure the length of this bar. 150.0 horizontally. 150.0, again, plus or minus 0.1 centimeter. So you would agree with me that I am capable of measuring plus or minus 1 millimeter. That's the uncertainty of my measurement. Now if the difference in length between lying down and standing up, if that were 1 foot, we would all know it, wouldn't we? You get out of bed in the morning, you lie down, you get up, you go plunk, and you're 1 foot shorter. And we know that that's not the case. If the difference were only 1 millimeter, we would never know. Therefore, I suspect that if my grandmother was right, then it's probably only a few centimeters, maybe an inch. And so I would argue that if I could measure the length of a foot into 1 millimeter accuracy, that should settle the issue. So I need a volunteer. You want a volunteer? You look like you're very tall, I hope that, yeah. I hope that we don't run out of, you're not taller than 178 or so? What's your name? Rick Ryder. You're not nervous, right? Oh. Man. Sit down. I guess that's all, guys. Here, come on. Please, more modest in size. Don't take it personal, Rick. Okay. Zach. Can I take today, Zach? Yeah? You feel right? First one to MIT? No, I don't. Okay, man. Stand there, yeah? Okay, 183 points. Stay there, don't move. Zach. This is vertical. What did I say? 180? Only one person. 3? Come on. 0.2, okay. 183.2, yeah. And the uncertainty of about this is centimeters, 0.1 centimeters. And now we're going to measure him horizontally. Zach, I don't want you to break your bones, so we have a little step for you here. Put your feet there. Oh, let me remove the aluminum part. Don't watch out for this scale, if you don't break that, because then it's all over. Okay, I'll come on your side if I have to do that. Yeah, relax. Think of this as a small sacrifice for the sake of size, right? No. Okay, are you good? You comfortable? You're really comfortable, right? Wonderful. Okay. You ready? Yeah. Okay. 185.7. Stay where you are. 185.7. I'm sure I want to make the subtraction, right? 185.7 plus or minus 0.1 centimeter. Oh, that is 5. That is 2.5 plus or minus 0.2 centimeters. You're about 1 inch taller when you sleep than when you stand up. My grandmother was right. She's always right. Can you get up here? I want you to appreciate that the accuracy, thank you very much, Zach, that the accuracy of 1 millimeter was more than sufficient to make the case. If the accuracy in my measurement would have been much less, his measurement would not have been convincing at all. So whenever you make a measurement, you must know the uncertainty, otherwise it is meaningless. Galileo Galilei asked himself the question, why are mammals as large as they are and not much larger? He had a very clever reasoning which I've never seen in print, but it comes down to the fact that he argued that if the mammal becomes too massive, that the bones will break. And he thought that was a limiting factor. Even though I've never seen his reasoning in print, I will try to reconstruct it, what could have gone through his head. Here is a mammal. And this is one of the four legs of the mammal. And this mammal has a size S. And what I mean by that is, a mouse is J big, and a cat is J big. That's what I mean by size. Very crucially defined. The mass of the mammal is N, and this mammal has a thigh bone, which we call the femur, which is here. And the femur, or it carries the body to a large extent. And let's assume that the femur has a length L, and has a thickness C. Here is the femur. This is what the femur approximately looks like. So this would be the length of the femur. And this would be the thickness, D. And this would be the cross-sectional area, A. I'm now going to take you through what we call in physics a scaling argument. I would argue that the length of the femur must be proportional to the size of the animal. That's completely plausible. If an animal is 4 times larger than another, you would need 4 times longer legs. That's all this is saying. Very reasonable. It is also very reasonable that the mass of an animal is proportional to the third power of the size, because it's related to its volume. And so if it's related to the third power of the size, it must also be proportional to the third power of the length of the femur, because of this relationship. Okay, that's one. Now comes the argument. Pressure on the femur is proportional to the weight of the animal divided by the cross-section A of the femur. That's what pressure is. And that is the mass of the animal, that's proportional to the mass of the animal divided by d squared. Because we want the area here, proportional to d squared. Now follow me closely. If the pressure is higher than a certain level, the bones will break. Therefore, for an animal not to break its bones, when the mass goes up by a certain factor, say a factor of 4, in order for the bones not to break, d squared must also go up by a factor of 4. That's a key argument in the scaling here. You really have to think that through carefully. Therefore, I would argue that the mass must be proportional to d squared. This is a grating argument. Now compare these two. The mass is proportional to the length of the femur to the power 3, and to the thickness of the femur to the power 2. Therefore, the thickness of the femur to the power 2 must be proportional to the length L, and therefore the thickness of the femur must be proportional to L to the power 3 mass. A very interesting result. What is this result telling you? It tells you that if I have two animals, and one is 10 times larger than the other, the S is 10 times larger. That the length of the legs are 10 times larger, but that the thickness of the femur is 30 times larger, because it is L to the power 3 half. If I were to compare a mouse with an elephant, would have to be 1,000 times larger. And that may have convinced Galileo Galilei that that's the reason why the largest animals are as large as they are, because clearly if you increase mass, there comes a time that the thickness of the bones is the same as the length of the bones. If you're all made of bones, and that is biologically not feasible. And so there is a limit somewhere set by this scaling law. Well, I wanted to bring this to a test. In fact, I brought my grandmother to a test, so why not bringing Galileo Galilei's statement to a test? And so I went to Harvard, where they have a beautiful collection of femurs, and I asked them for the femur of a raccoon and a horse. A raccoon is this big, a horse is about 4 times bigger, so the length of the femur of a horse must be about 4 times the length of the raccoon. Close. So I was not surprised. Then I measured the thickness, and I said to myself, aha, if the length is 4 times higher, then the thickness has to be 8 times higher if it is holes. And what I'm going to plot for you, you will see that shortly, is G divided by L versus L. And that, of course, must be proportional to L to the power 1/2. I bring 1 L here. So, if I compare the horse and I compare the raccoon, I would argue that the thickness divided by the length of the femur for the horse must be the square root of 4, twice as much as that of the raccoon. And so I was very anxious to plot that, and I did that, and I'll show you the result. Here is my first result. So, we see there G over L. I explained to you why I prefer that to plot it, and here you see the length. You see here the raccoon, and you see the horse. And if you look carefully, then the G over L for the horse is only about 1.5 times larger than the raccoon. Well, I wasn't too disappointed. 1.5 is not 2, but it is in the right direction. The horse clearly has a larger value for G over L than the raccoon. I realized I needed more data, so I went back to Harvard. I said, look, I need a small animal, an opossum maybe a rat, maybe a mouse. And they said, okay. They gave me 3 more bones. They gave me an antelope, which is actually a little larger than a raccoon, and they gave me an opossum, and they gave me a mouse. Here is the bone of the antelope. Here is the one of the raccoon. Here is the one of the opossum. And now you won't believe this. This is so wonderful, so romantic. There's the mouse. Isn't that beautiful? Teeny weeny little mouse with only a teeny weeny little femur. And there it is. And I made a plot. I was very curious what that plot would look like. And here it is. I was shocked. I was really shocked. Because look, the horse is 15 times larger in size than the mouse. The difference in G over L is only a factor of 2. And I expected something more like a factor of 7. And so in G over L, where I expect a factor of 7, I only see a factor of 2. So I said to myself, oh my goodness, why didn't I ask them for an elephant? The real treasure would be the elephant, because if that goes way off scale, maybe we can still rescue the statement by Galileo Galilei. And so I went back, and they said, okay, we'll give you the femur of an elephant. They also gave me one of a moose, believe it or not. I think they wanted to get rid of me by that time, to be frank with you. And here is the femur of an elephant. And I measured it, the length and the thickness. And it is very heavy. It weighs a ton. I plotted it. I was full of expectation. I couldn't sleep all night. And there's the elephant. There is no evidence whatsoever that G over L is really larger for the elephant than for the mouse. These vertical bars indicate my uncertainty in measurements of thickness, and the horizontal scale, which is a logarithmic scale, the uncertainty of the length measurements is in the thickness of the red pen, so there's no need for me to indicate that any further. And here you have your measurements, in case you want to check them. And look again at the mouse and look at the elephant. The mouse has indeed only 1 centimeter length of the femur, and the elephant is indeed 100 times longer. So the first scaling argument, that S is proportional to L, that is certainly what you expect, because the elephant is about 100 times larger in size. But when you go to G over L, you see it's all over. The G over L for the mouse is really not all that different from the elephant, and you would have expected that number to be with the square root of 100, so you expect it to be 10 times larger instead of about the same. I now want to discuss with you what we call in physics dimensional analysis. I want to ask myself the question, if I drop an apple from a certain height, and I change that height, what will happen with the time for the apple to fall? Well, I drop the apple from a height h, and I want to know what happens with the time when it falls. And I change h. So I said to myself, well, the time that it takes must be proportional to the height to some power alpha. It's completely reasonable. If I make the height larger, we all know that it takes longer for the apple to fall. That's the safe thing. I said to myself, well, if the apple has a mass m, it probably is also proportional to the mass of that apple to the power beta. I said to myself, gee, yeah, if something is more massive, it will probably take less time. So maybe m to some power beta. I don't know alpha, I don't know beta. And then I said, yeah, there is also something like gravity, that is the Earth's gravitational pull, the gravitational acceleration of the Earth. So let's introduce that too, and let's assume that that sign is also proportional to the gravitational acceleration. This is an acceleration, we'll learn a lot more about that, to the power gamma. Having said this, we can now do what's called in physics a dimensional analysis. On the left, we have time. And if we have on the left side of time, on the right side we must also have time. You cannot have coconuts on one side and oranges on the other. You cannot have seconds on one side and meters per second on the other. So the dimensions left and right have to be the same. What is the dimension here? That is t to the power 1. That's t. That must be the same as length to the power alpha times mass to the power beta times acceleration. Remember, it is still there on the blackboard, has dimension L divided by time squared. And the whole thing to the power gamma, so I have a gamma here and I have a gamma there. But this side must have the same dimension as that side. That is non-negotiable in physics. Okay, there we go. There is no m here, there is only one m here, so beta must be 0. There is here L to the power alpha, L to the power gamma, there is no L here, so L must disappear, so alpha for gamma must be 0. There is t to the power 1 here, and there is here t to the power minus 2 gamma. It's minus because it's downstairs. So 1 must be equal to minus 2 gamma. That means gamma must be minus 1/2. That if gamma is minus 1/2, then alpha equals plus 1/2. End of my dimensional analysis. I therefore conclude that the time that it takes for an object to fall equals some constant, which I do not know, but that constant has no dimension, I don't know what it is, times the square root of h divided by g. Beta is 0, there is no mass, h to the power 1/2, you see that here, and g to the power minus 1/2. So this is proportional to the square root of h, because g is a given and c is a given, even though I don't know c. I make no pretense that I can predict how long it will take for the apple to fall. All I'm saying is, I can compare two different heights. I can drop an apple from 8 meters, and another one from 2 meters, and the one from 8 meters will take 2 times longer than the one from 2 meters. The square root of h to 2, 4 over 2 will take 2 times longer, right? If I drop one from 8 meters, and I drop another one from 2 meters, then the difference in time will be the square root of the ratio that will be twice as long. And that I want to bring to a test today. We have a setup here. We have an apple there at a height of 3 meters. We know that actually the length to an axis is a height of about 3 millimeters, no better. And here we have a setup whereby the apple is about 1.5 meters above the ground, and we know that to about also an accuracy of no better than about 3 millimeters. So let's set it up. I have here something that's going to be a prediction of the time that it takes for one apple to fall divided by the time that it takes for the other apple to fall. H1 is 3 meters, but I claim there is an uncertainty of about 3 millimeters, can't do any better. And H2 equals 1.5 meters, again with an uncertainty of about 3 millimeters. So the ratio of H1 over H2 is 2.000, and now I have to come up with an uncertainty, which physicists sometimes call an error in their measurements, but it's really an uncertainty. And the way you find the uncertainty is that you add the 3 here, and you subtract the 3 here, and you get the largest value possible. You can never get a larger value. And you'll find that you get 2.006. And so I would say the uncertainty is then 006. This is a dimensionless number because it's length divided by length. And so the time t1 divided by t2 would be the square root of h1 divided by h2. That is the dimensional analysis argument that we have there. And we find, if we take the square root of this number, we find 1.414 plus or minus 0.0, I think that is a 2. That's correct. So here is a firm prediction. This is a prediction. And now we're going to make an observation. So we're going to measure T1, and there's going to be a number, and then we're going to measure T2, and there's going to be a number. I have done this experiment 10 times, and the numbers always reproduce within about 1 millisecond. So I could just adopt an uncertainty of 1 millisecond. I want to be a little bit on the safe side. Occasionally it differs by 2 milliseconds. So let us be conservative, and let's assume that I can measure this to an accuracy of about 2 milliseconds. That is pretty safe. So now we can measure these times, and then we can take the ratio, and then we can see whether we actually confirm that the time that it takes is proportional to the height, to the square root of the height. So I will make it a little more comfortable for you in the lecture hall. That's alright. We have the setup here. We first do the experiments with the 3 meters. There you see the 3 meters. And the time. The moment that I pull this string, the apple will fall, the contact will open, the clock will start, the moment that it hits the floor, the time will stop. I have to stand on that side, otherwise the apple will fall on my hand. That's not the idea. Here. You ready? Okay, then I'm ready. Everything set? Make sure that I zeroed that button. Yes, I have. Okay, 3, 2, 1, 0. 781 milliseconds. So this number, you should write it down because you will need it for your second assignment. 781 milliseconds with an uncertainty of 2 milliseconds. We're ready for the second one. You ready? You ready? Okay, nothing wrong. Just being ready. 0, 0, right? Thank you. Okay, 3, 2, 1, 0. 551 milliseconds. Boy, I'm nervous because I hope that physics works. So I take my calculator and I'm now going to take the ratio T1 over T2. The uncertainty you can find by adding the 2 here and subtracting the 2 there, and that will then give you an uncertainty of, I think, 0.08. Yeah, 0.08. You should do that for yourself. 0.008. Dimensionless number, this would be the uncertainty. This is the observation. 781 divided by 551. 1 point, let me do that once more. 781 divided by 551. 1,417. Perfect agreement. Look, the prediction says 1.414, but it could be 1 point, could be 2 higher. That's the uncertainty in my height. I don't know any better. And here, I could even be off by an 8, but that's the uncertainty in my timing. So these 2 measurements confirm they are in agreement with each other. See, uncertainties in measurements are essential. Now, look at our result. We have here a result which is striking. We have demonstrated that the time that it takes for an object to fall is independent of its mass. That is an amazing accomplishment. Our great-grandfathers must have worried about this and argued about this for more than 300 years. Were they so dumb to overlook this simple dimensional analysis? Inconceivable. Is this dimensional analysis perhaps not quite crucial? Maybe. Is this dimensional analysis perhaps one that could have been done differently? Yeah. Oh yeah, you could have done it very differently. You could have said the following. You could have said the time for an apple to fall is proportional to the height that it falls from to a power alpha. Very reasonable. We all know the higher it is, the more it will take, the more time it will take. And we could have said, yeah, it's probably proportional to the mass somehow. If the mass is small, it will take a little bit less time. It turns out to be not so, but you could think that. But you could have said, well, let's not take the acceleration of the Earth, but let's take the mass of the Earth itself. Very reasonable, right? I would think if I increase the mass of the Earth, that the apple will fall faster. So now I would put in the mass of the Earth here. And I start my dimensional analysis, and I end up dead in the waters. Because you see, there is no mass here. There is a mass to the power beta here and 1 to the power gamma. So what you would have found is beta plus gamma equals 0, and that would be end of story. Now you can ask yourself the question, well, is there something wrong with the analysis that we did? Is ours perhaps better than this one? Well, it's a different one. We came to the conclusion that the time that it takes for the apple to fall is independent of the mass. Do we believe that? Yes, we do. On the other hand, there are very prestigious physicists who even nowadays do very fancy experiments, and they try to demonstrate that the time for an apple to fall does depend on its mass, even though it probably is only very small if it's true, but they try to prove that. And if any of them succeeds, or any one of you succeeds, that's certainly worth a Nobel Prize. So we do believe that it's independent of the mass. However, this, what I just presumed, was not a proof, because if you do it this way, you get stuck. On the other hand, I'm quite pleased with the fact that we found that the time is proportional with the square root of h. I think that's very useful. We confirmed that with experiments, and indeed, it came out that way. So it was not a complete waste of time. But when you do dimensional analysis, you better be careful. I'd like you to think this over, the comparison between the two, at dinner, and maybe at breakfast, and maybe even while you're taking a shower, whether it's needed or not. It is important that you digest and appreciate the difference between these two approaches. It will give you an insight in the power and also into the limitations of dimensional analysis. This goes to the very heart of our understanding and appreciation of physics. It's important that you get a feel for this. You're now at MIT. This is the time. Thank you. See you Friday. We will discuss velocities and acceleration. I'll start with something simple. I have a motion of an object along a straight line. We'll call it non-dimensional motion. And I'll tell you that the object is here at time t1, at time t2 is here, at time t3 is there, time t4 is here, and at time t5 is back where it was at t1. And here you see the positions in x where it is located at that moment in time. I will define this to be the increasing value of x. It's my free choice, but I've chosen this now. Now we will introduce what we call the average velocity. I'll put a bar over it, that stands for average, between time t1 and time t2. That we define in physics as x as time t2 minus x at time t1 divided by t2 minus t1. That is our definition. In our case, because of the way that I define the increasing value of x, this is larger than 0. However, if I take the average velocity between t1 and t5, that would be 0 because they are at the same position. So the upstairs is 0. If I had chosen t4 and t2, average velocity between time t2 and t4, we would have seen that that is negative because the upstairs is negative. Notice that I haven't told you where I choose my 0 on my x-axis. Completely unimportant for the average velocity. It makes no difference. However, if I had chosen this to be the direction of increasing x, then, of course, the signs would flip. Then this would have been negative, and this would have been positive. So the direction that you are free to choose determines the signs. The location where you put your 0 is not important, but signs in physics do matter. Signs are important. Whether you owe me money or I owe you money, the difference is only a minus sign. But I think it's important for you. Now I will give you not only the positions as I did here on the x-axis at discrete moments in time, but I'm going to tell you exactly where the object is at any moment in time. Here you see an xt diagram. So you see that at t1, the object is at position xt1. This is the road of the object. This is the straight line that's moving. It starts here, and it goes to this position, it goes to this one, it comes back to t4, and it comes back here. I will tell you now every moment in time in between. There it goes. Voila. This is now information that is way more. You have the information at any moment in time. Notice that I now did choose x equals 0. I chose it somewhere here. But I could have chosen it at any other point. For river follows, you will see that it makes no difference. So I have chosen the 0 point so that I can make the graph. And now we will look at the average velocity in a somewhat different way. Say I choose my time t2 and t3. I draw here now this line. At this angle I call alpha. And this part here I call delta x. And this here is delta t. And so you could write down, if you're careful about your sign convention, you could write down now that the average velocity equals delta x divided by delta t. But, be careful, if the angle is positive, I call this a positive angle, then the average velocity is positive, but if I have a negative angle, then the average velocity would be negative. For instance, between t4 and t5, if I draw this line, then this angle here is negative, and so the average velocity between t4 and t5 is now negative. Again, if I had changed the 0 points, you would have found the same values for the average velocity. The only difference would have been the position of the curve in that plot. There's a very big difference in physics between speed and velocity. The average velocity between time t1 and t5 is 0, but the average speed is not. The average speed is defined as the distance traveled divided by the time that it takes to travel that distance. What is the distance that the object travels between time